So first of all, just a word of warning, do not try this one at home. This is day 2. Started off a bit flippantly with just grabbing any old water in any old bottle. Upped the level a little bit and got proper demineralized, deionized water. Again, was just using secondhand bottles. Started to get a data logger in an infrared thermometer. Went to the science lab. Still getting it not to freeze or to freeze too quickly. Day 3, moved to the office where I'm working a lot, so I could just keep going forever and ever until I got it to work. There are new bottles there, still purified water, nice and smooth. Lots of fail videos on this on the website. You can see the ones that succeed end up using lots of bottles. And so I think that's probably the biggest hack. I would use a new bottle with smooth surfaces, a lot of them using Fiji bottles, but we didn't have any in the supermarket at the time. So I got the smoothest bottles I could get. And then the other thing, I did use purified water. Going by the temperature measurements, I could only get it to about -2 before it freezes up. So you can't really get it to -8. I don't know, maybe you can. And so every freezer freezes at different rates, and the waters are slightly different, and there might be more nucleation sites on a scratched or older bottle or a newer bottle that has more surfaces, so it might freeze easier. The water will attach to it. So very frustrating, but the key hack, I think, is having lots of bottles. And so hopefully one bottle will start freezing before the rest, and then you know at your limit. And so one of those bottles was actually frozen, as opposed to all of the bottles. I think if I waited like one more minute, the whole lot would freeze. So that's how frustrated it is. And so you can just see that I managed to get the super cooled. Okay, so what the heck is that about? So this is about freezing water and sort of that trick in making it instantaneously freeze. Okay, so what's going on there is the water molecules are actually meant to freeze, but they haven't lined up. So if you just bump the freezer, so bumps as well are included, or any disturbance, you only get one shot at this, it will freeze because it really wants to freeze. Okay, so what's going on is the water molecules are actually lining up. Now we know they line up actually in this hexagon sort of structure. There's 5 hydrogen bonds. So the water itself has, the red is oxygen, which is negative, and the white's hydrogen, which is positive. So the oxygen steals more electrons to its side, so it becomes slightly negative, and the hydrogen becomes slightly positive. And so the pos and neg areas attract each other, and so that's where we get the stickiness words from. So the proper term for that is actually hydrogen bonds. Sometimes I just say stickiness if it's junior science. So positives attract to neg. And when we use the word hydrogen bonds, it's just trying to give us an idea of the strength of the pos and neg. So really it's just a pos and neg, and hydrogen bond is just an English word to give us some sort of mathematical value of strength. I think it's somewhere between 10 and 40 kilojoules per mole is a more accurate. Don't hold me to that. I didn't research that. I'm just doing that off the top of my head. But we use these English words, and if you look behind them, there will be actually mathematical values which are far better, and you'll have to look at the specific molecule to know the real number. Okay, so what's going on is they form these different structures. Now, if you look at the research in the past, this website's quite good because it goes all the way back to 1884. Now, they've always known that there is what they're now calling an expanded and a collapsed structure. And there's various forms of it, and it's getting more and more complicated. But we know that one has spaces and one doesn't. And we know they form a 6 ring, because if you I'll put it in the description, the link to the Veritasium video where they one physics professor from a top university has actually precisely worked out how to change the shape of ice crystals and exactly how the crystals form, and can change the temperature and densities to design crystals and repeat them and make snowflakes that are pretty much exactly the same repetitively. So they've sort of mastered that now. He's a very intelligent guy. And so what I'm just demonstrating here is the collapse structure here, where the kinetic energy is so much that it just rolls, it breaks all the hydrogen bonds and they roll over each other. And now what I'm trying to do is trying to make the expanded structures now. So I'm trying to make the 6 waters match up, and then a little bit more difficult is when I just try and get a couple of those and match them up to get them to join up to make the more advanced, basically forming the ice. And so all the kinetic energy is removed, and so that there is not so much energy to break all these hydrogen bonds, and the hydrogen bonds can stick, and so it becomes expanded. Now, there's only one other substance. I think there's others, but gallium, I found out, is another one. So it becomes less dense when it's ice and it floats. So I did a video on gallium. Before that, I wasn't really aware. I know there are, but they're really obscure. Substances that are less dense when they become a solid. So if you look at the diagram here, that kind of shows that. So you can see that around 0, if you go less than 0 and it becomes ice, it becomes less and less dense because you're forming these expanded structures and removing heat. And around 0, where it becomes water, so now your expanded structures plus heat. And so the heat is breaking the hydrogen bonds and it's collapsing on itself. So it's going to the right this time. And becoming a collapsed structure, water. And then it starts to increase in density again as it goes from 0 to 100. It decreases in density from 0 to 100 because of thermal expansion. So because there's so much kinetic energy and the particles bumping into each other, the spaces in between the particles increases. So to the right, it's the density decreases because of thermal expansion, but to the left, the density decreases due to the expanded structures, the spaces between them due to the formation of hydrogen bonds that remain because there's not enough kinetic energy to break them. And just interestingly, if you just zoom in, you'll see that actually there's a little bit of a gap. So the highest density is around like 4 to 5 degrees here if you zoom in on that. And so there's some between 0 and 5, even though it's water, there would be obviously some loss of sufficient kinetic energy to form some sort of expanded structures within the water, but it still flows over each other and it's not all locked up in place. So water is quite complicated, as you could have seen from the proposed structures. Some even have considered that there's 2 types of waters. So we'll leave that to the professors to worry about. All right.